Hi and welcome to this tutorial, which is slightly different as we're not modeling a typical beam that we would encounter in the bridge industry, but we rather modeling here a geometry that is more applicable to the architectural industry. We're modeling a beam which is half circular. So uh, this is something that you can have, for example, there's this structure over the Grand Canyon, but you can think as well as some curved beams uh, at the corners of a building, if you have maybe a terrace, a balcony, or something like this. So anyway, this is the process to model such a geometry. There is a trick that I will show you, and I think this is quite useful for these applications, so why not? So we have a curved, it's not really a bridge, just a curved beam. We're not modeling the concrete deck, so it's just erection analysis here. It's going to be very simple, okay? I have special DOF fixities to restrain bending and torsion. I have point loads, and that's about it. So quite a simple example here. The radius of curvature here, you see, it's extremely tight. It's just 10 feet. I have This is 10 feet, right? And the limitation usually of this, if you're not selecting this compound curvature option, is to have a subtended angle, which is limited to 90 degrees. If you want to go half circle, you would need to check yes here. You need to select yes for the compound curvature. And so the compound curvature means that really the geometry will be defined in two stages. We have one girder, one beam, which is about 30 foot long. And so this is the form for the compound curvature. We're saying that the length of the arc with the initial curvature of 10 feet is equal to half the length of the beam. And the final radius of curvature is going to be equal to the initial radius of curvature, okay? This is a trick to be able to go over that 90-degree angle limit that we would have otherwise, okay? And for most bridges, the subtending angle is never more than 90 degrees. It's more like maybe 30 degrees or 40 degrees, maybe 50 degrees, but going over 90 degrees is very rare. But if you are in such a situation, this is the trick. You would select the compound curvature and having a final radius of curvature which is equal to the initial radius of curvature. Now, you also have cases where the final radius of curvature is in effect different, maybe smaller, maybe bigger, and so here you would enter something different, okay? We are using standard material properties for the steel. We are defining 12 special fixities at nodes number 2 and 8 of the section, so at the bottom flange and the top flange, and at 0 and 31.4, so really at both ends of the beam. We are restraining the three directions, so 1, 2, and 3, X, Y, and Z. And we could click on this button again, but this model was already saved and reopened, so we don't need to here. We haven't changed any of the reference points. We have quite a fine mesh. Okay, this is a tiny system, so why not define really a really fine mesh with 4 inches as the mesh size in the longitudinal direction, and 8 would be the number of elements through the web depth. Okay, this is a tiny mesh that we would never consider such a mesh for a large, complex bridge. We have just one cross-sectional profile, okay, for simplicity here. The web depth is about 20 inches. We are, of course, using that profile for both segments. We are turning on the whole length of the beam. And just as an example, why not define a point load at midspan acting on the top flange node, so that's node number 8, and acting in the vertical direction, so that's direction Z or 3. And let me go back here. That's here. So -1 kip would be a unit load acting in the vertical direction at that node. We are not turning on the self-weight. We could, of course. This is just a very simple example to see what's the behavior of that semicircular beam under a point load at midspan. We can run the analysis. It takes a few seconds to run, about less than 10 seconds. Let's maybe reduce the size of the arrow for the load. Let's reduce the size of the supports here. Let's zoom in a little bit. Let's move the model around slightly. Okay, here we go. We've got the plate thicknesses as defined. And now let's look at the linear elastic solution. You can see that the maximum displacement is equal to about 0.4 inch. So about 1 centimeter. That would be in SI units. We can look at the von Mises stresses or the sigma y stresses, and we can see the lateral bending which is occurring really along the length of the beam here in kind of waves. Okay, we can see this pattern here and then there on both flanges. We can also look at other stress components, so that would be sigma xy, so it's kind of a torsion on the flanges. This is the envelope, okay, so it's always positive. If we want to look at the top face, we would select 2 here, 2 sigma xy top face. We can also look at the sigma yz stress, which is kind of the stress, torsional stress on the web. Other things we can look at are some charts. We can plot some charts. This is the displacement of, so displacement component 3. So that's really the z or vertical component of the displacement vector at cross-sectional node number 2. So that would be this node here, the bottom flange. We can look at the layovers. So that's the relative displacement in inches between the top flange and the bottom flange. And we can of course look at the moment diagram. Okay, the zeros here are not due to stress concentrations or anything. It's just by default, in general, for bridges we are enforcing 0 at the ends. Okay, this is most of the time the case. So really, this is don't really worry too much about this inconsistency. The moment at the end is about is equal to about minus 60 kip inch. Okay, and same on the other end. So it follows a linear pattern, which is as expected because we have a point load, not a distributed load, and it is symmetrical here. Okay, now if we look at the shear diagram, okay, again we can see it's we can see this step, and we can see that the depth of the step is equal to 0.5 minus 0.5, so 0.5 plus 0.5, which is 1 kip, which is the load that we have applied. So again, this is as expected. We're going to also look at the torque diagram, which is pretty smooth here, okay, pretty smooth, and the top flange lateral diagram and the bottom flange lateral diagram. And we can see again the waves that we were seeing visually in the viewer directly on the beam. Something else that maybe we can look at is another type of graph, which is the principal versus the lateral bending stress. And again, we can see here that the bending stress is actually much lower than the lateral bending stress. Okay, this is because of the extremely tight curvature of the beam. So I hope this example was useful. Again, this is not something that we would see typically on a bridge, but rather in the architectural industry. I hope nonetheless that this can be useful on your projects. Thank you for your